New York City just plugged an extension cord into Canada. It's 339 miles long. It's buried the entire way, under a lake, under the Hudson River, under city streets, and you could stand directly on top of it and never know it's there. It now carries close to a fifth of the electricity in America's largest city. It's called the Champlain Hudson Power Express. It cost about $6 billion, and it is the longest fully buried power line in North America. And for a few weeks this summer, at the exact moment New York needed it most, it went completely dark. To understand why that mattered so much, and why a city of 8.5 million people is now leaning on a single cable, you have to understand what this line actually is and the strange engineering choice buried underneath it. Start at the top. Near Montreal, the line connects to Hydro-Quebec, the utility that runs one of the largest hydroelectric systems on Earth, a fleet of dams pouring out clean, cheap power. From a substation there, the cable heads south toward New York, and for all 339 miles, it never appears as the towers and wires you picture when you think of a transmission line. It goes underground and underwater almost the entire way. It runs along the bottom of Lake Champlain. It's buried beside railroad tracks and highways. And for a long stretch, it lies in a trench dug into the bed of the Hudson River. Roughly half of the route, more than 200 miles of it, is underwater. The rest is buried in the ground. At the New York end, it surfaces in Astoria, Queens, at a converter station wired straight into the city's grid. 2 cables, each about as thick as a grapefruit, carrying 1,250 megawatts into the heart of New York. That's enough to power more than 1 million homes, about 10 terawatt-hours a year, close to 20% of New York City's entire electricity supply, delivered through a wire you will never see. Which raises an obvious question. Why on earth would you bury a power line for 339 miles? Burying transmission is enormously expensive and difficult. Normally you string a power line up on towers, because air is a free insulator. Hanging the wire in open space is the cheapest way to keep it from shorting out. New York went underground for a blunt reason. For decades, nobody could get an overhead line through. Above-ground towers across the Adirondacks, along the lake, and down the Hudson Valley meant lawsuits, permitting fights, and communities that simply did not want them in the view. Bury the line, and most of that opposition disappears. You can't object to what you can't see. But burying a line for hundreds of miles creates a brand new problem. And it's the reason this cable carries direct current, DC, instead of the alternating current running through almost everything else on the grid. Here's the issue. A long underground AC cable behaves like a giant capacitor. The metal conductor and the earth around it store and release electric charge 60 times a second, and that sloshing charging current gets bigger the longer the cable runs. Push past a few dozen miles of buried AC cable, and so much of the line's capacity is eaten up just charging and discharging itself that there's almost nothing left for delivering real power. Long-distance buried AC simply doesn't work. Direct current doesn't swing. It flows steadily in one direction, so there is no charging current, no matter how long the cable is. That's why nearly every long buried or undersea power link in the world is HVDC, high-voltage direct current. The catch is that you need 2 expensive converter stations, one at each end, to turn the grid's AC into DC for the trip and back into AC on arrival. Over 339 buried miles, that trade-off is easily worth it. And there's a second reason DC fits here. Quebec's power grid and the eastern US grid don't actually run in step with each other. They're 2 separate machines, humming to their own beat. You can't just bolt them together with an AC wire without them fighting. A DC link acts as a controlled gateway between the two. It dials in exactly how much power flows, and in which direction, on command. It's a one-way valve between 2 independent grids. So why would New York want 1,250 megawatts of Canadian hydropower badly enough to spend $6 billion burying a cable to get it? 2 words, Zone J. New York City is its own electricity zone. The grid operator literally calls it Zone J. and it is the most congested, most expensive corner of the entire state power system. It's a dense island of demand fed by a limited number of wires and a fleet of mostly old, in-city gas plants. Electricity there has long been some of the priciest in the country, precisely because it's so hard to get more power into it. For years, the city couldn't easily pull in cheaper power from upstate, because the transmission lines running down to the city were already packed full. The Champlain Hudson Power Express is a brand new highway that goes around all of that, running straight from Quebec's dams into the middle of the load pocket and bypassing every bottleneck in between. And the payoff is real. Cleaner power displacing fossil generation. Lower wholesale prices in the most expensive zone in the state. A serious step toward New York's climate targets. On paper, it is exactly the kind of infrastructure the grid is supposed to want. And then came July. The line entered full commercial service in the spring of 2026, actually ahead of schedule. Power started flowing into the city on the 1st of June. And for its first month, it did exactly what it promised. Then on the 4th of July, in the middle of a heat wave, the Champlain Hudson Power Express tripped offline. All 1,250 megawatts, a fifth of the city's supply, vanished from New York in an instant, on one of the hottest, highest demand days of the year. The precise scenario the line had been built to protect against. The cause was a fault in the buried cable on the New York side of the route. And here is the hard part about a buried line. When an overhead wire fails, crews can often see the damage and repair it in hours. When a cable is entombed in a trench underground, they first have to find where the fault is, then dig down to reach it, then cut out the damaged section and splice in a new one. So it did not come back in hours. Electricity did not flow through the line for more than 10 days. The repairs stretched on for weeks. Through most of July, the city's newest and cleanest source of power sat dark, and New York leaned right back on the same expensive gas plants the cable was supposed to relieve. The line was scheduled to return to service around the 1st of August, but the outage had already exposed something the ribbon cuttings never mentioned. The great strength of this project is also its weakness. 20% of a megacity's electricity concentrated into one line, buried exactly where it is hardest to reach. When it works, it's a clean, quiet, invisible river of power. When it fails, a fifth of the supply doesn't dim, it disappears all at once. That's the trade-off baked into big, singular pieces of infrastructure. 100 small power plants scattered across a city tend to fail one at a time. One giant cable fails all at once. New York traded a diffuse, dirty, expensive supply for a concentrated, clean, cheap one, and it inherited a concentrated risk right along with it. None of that means the line was a mistake. Every grid on Earth runs on a handful of big, critical assets, and this one delivers exactly what it promised whenever it's actually running. But it's a reminder that resilient and efficient often pull in opposite directions, and that the cleanest, cheapest option is not automatically the sturdiest one. New York now has one of the most impressive pieces of transmission ever built running silently beneath its rivers and its streets. Whether a single cable, however remarkable, is a solid foundation to build a city's power supply on, or a quiet single point of failure the grid has grown to depend on without quite admitting it, is a question the first hot week of every summer from here on out is going to keep asking.